Welcome to AGEC 685. This is Module 2, the first lecture material we're going to cover. In this module we will start thinking about optimization more formally. We've talked about it a little bit prior to this, but mostly been thinking about model sort of setup and formulation. Here we are getting into economics and sort of the guts of economics, the thing that makes it all work, and it's obviously one of these sort of key debate avenues in economics is whether people and agents and firms and all of these are able to accurately optimize, and whether you believe that or not, it still has served as a very good sort of organizing principle. Okay, and so we are going to, in this module, as one of our primary objectives, think about the importance to economic analysis of optimization, familiarize ourselves with techniques, mostly to help us understand the outputs. When we solve an optimization problem, when we get the result, what kind of context can we attach to that? And then we need to know about the economic content in an optimization solution. It is the case that we are abstracting from all the sort of complexity that might influence a decision, and so we have to be prepared to think about not just our solution, but any kind of sensitivity, and that's where we'll be working our way up to. Okay, by way of overview, we'll do a sort of an introduction to optimization, and then we'll actually do sort of a classic problem. Given that this cohort is also in a trade/macro of agriculture class, I think it's a fun one to start with, the sort of classic GDP problem, if we could split everything into two different kinds of output. From there, we'll move on to linear approximation and continue our work on implementation, which was our week one topic, our module 1 topic. Then we'll go on to analysis, thinking about solutions and corner points, and then finally, in the last bit of this module, in the last lab, we'll talk about minimization, and that will be your way into thinking about the project work. So the part of this module assignment that goes toward producing that project deliverable. In economics, optimization is our guiding principle, and of course that begs the question, why? It is certainly not to say that we need to get the right answer, or we need to figure out or design or come up with answers that we can prove to be best, But we need something, right? We need something that we can all sort of agree on or sort of formulate our problems around. And heuristics, the idea that people have a tendency to continue to do the same thing over and over, if you will, sort of classical Newtonian physics has its three principles, and one of them is inertia, and things tend to stay in motion unless they're acted upon. Well, we have something similar to that, except if we just started from the idea that people make these choices, we wouldn't know how to think about how they adjust when forces do act upon them. So just like in physics, they need to know what happens when a pool ball at rest is struck by the cue ball, and figure that out. We need to think about how a decision that someone has made would be influenced when something happens. And so really economics is fundamentally about sort of a behavioral analysis, understanding how responses happen. So we sort of start from the idea that people can classify things, classify events, or classify purchases, or classify their economic options into those that are preferred and those that aren't. And if they're doing well, if they're able to process information and make those decisions, then then that gives us optimization as sort of a guiding principle, and then that lets us think about if they're optimizing in the initial case when we observe someone, then we can think about what is their response going to be when the economy or the trade policy or labor policy or some new regulation or the removal of a regulation on utilities, however we want to think about it, whatever kind of action that could happen that the person has no control over, the agent has no control over, it gives us a way of thinking about how they respond. And so in some ways, every problem, even though we tend to think about markets when we talk about equilibrium or even bigger sort of sections of the economy, equilibrium or stability, again, to borrow from sort of the Newtonian physics, is something that is critical to our understanding. In economics, we almost always think about the optimization or the optimal solution being something that has already been done. Someone has the choices, they took the position they want, they have the income they're earning based on their best option for employment, and then they spend that money given all their thoughts about future versus now consumption and all the sort of consumption options that they have now. And so if we can do that, then we can think about this being the stable point. So they start from an equilibrium, there's no tendency to change, and only when conditions do change will they have to make adjustments. And as long as we are able to sort of capture what the change was and what we believe the preferences or the sort of behavioral guidelines that got them to the original choice, then we can think about how they might optimally adjust. Okay, so an optimum is a type of equilibrium. It is a setting, if you will. A decision maker that is optimizing has no incentive to change. Okay, so the idea being, if you've already made your best choice, then we wouldn't expect you to make an adjustment to it on a whim. If the adjustment was better and nothing else happened, right? If no other change in the economy happened, then why weren't you doing that before, right? So what is it corrective to? And that lets us think about, there's a shock to prices or a change to prices. How is this firm going to come up with a new best plan? Or think about alternatives. Under many different potential price patterns, what range of choices should be considered and can be argued as best under those? And obviously, those are the kind of, the second one question here is where we get things like the supply curve from. Tell me all the possible prices and I'll tell you what the sort of best output level will be. And sitting underneath that is an optimization problem. Okay, so if we back our way up to Economics 101 and think about an example we might have seen, you could see something like this. So a firm selling units, and they have this table of choices. They could sell 1 up to 7. And then we just say that the market gives them $5 for every unit sold, so that total revenue gets measured here as 5 times the units sold. And then we have their cost information. So they've gone through, and the engineering department or whoever is monitoring this tells us these are the cost levels that will be incurred for each of these output levels. And so you can see this, while this one is increasing by 5 for every unit of output, the costs are going up quicker. And so with a total revenue and a total cost, all we need to do is think about the increments. How do these change? And that gives us something like that we can do economic analysis for the change in revenue, the change in cost, or if you will, the marginal revenue and the marginal cost. Economics 101, they taught you, they taught us, they taught everyone, set marginal revenue equal to marginal cost, and you know that you're getting the best choice. And to prove that, you come out here and you calculate total revenue minus total cost and see where it's the largest. And you see here we have this small problem. In a problem where we have to produce either 1 or 2 or 3, we can't go in between 4 and 5 and pick the right number of units, the right partial number of units. We can't always make the change in revenue equal to change in cost, but we could come up with a condition that says We want marginal revenue to be equal to marginal cost, and if we can't find that, then find the place where marginal cost is closest to marginal revenue without exceeding it. And so that's sort of the classic introduction to that. If we plotted that out, that, by the way, that spreadsheet is available for the marginal revenue, marginal cost. If you want to follow through these calculations, it is in your module spreadsheet. This graphic is not, but you could certainly plot it if you want. If we were to track and to plot the marginal cost, the change in cost curve, and the change in revenue curve here, we would see that the change in revenue is the blue line here. We would see that they cross about right here, and so it is telling us that we would like to plot, that we would like to be in between 4 and 5. And because we plotted this profit, just the ones we measured, and at 5 they're too low, the profit curve seems to find its peak right here. But this information right here is telling us that a true picture of the profit would probably continue to rise until we got right there. Okay, we have incomplete information. Anytime we have these sort of discrete problems, we don't have sort of the smooth curve that has that you could take a derivative of. These sort of discretized tables, then we don't get the classic results from economics. If you want to get the classic results from economics, you need to write a calculus problem out. And so let's do that. Let's do the classic profit max problem, and you can follow through on this one. I'll show you a graphic of it at the end. If you want to do the math, you can follow along. The objective: maximize the profits by sales of some product represented by Q and sold at price P. And then a key result here is, or a key assumption, we're going to say that the price can be set by the producer. Note that producer setting the price is not the price taking assumption, not something that we typically adopt. So if that bothers you, that's okay. The math still works, but we're assuming we have a price setting seller here. Some assumptions: that we'll say the demand is linear, that price and quantity are inversely related. That means demand is downward sloping. And we have some information that says when consumers can get this item for free, they'll buy 10 units. When they can get it, when the price is set at 5, only 5 units will be bought. That is enough information to construct the demand curve, given that we've been told it's linear. And we obviously can see that there's inverse relationship. So if you want, figure it out, but I'll just tell you the demand curve must be 10 minus P. We have 2 points, so we know it's linear, and we can have 2 points, so we know we can find the slope and intercept. That's all it takes to recover that information. We needed some additional assumptions, though. If we're going to solve a profit maximization problem, we need to know that cost information. We need to know how costs are changing when quantity adjusts. And so I'm just going to give you the cost function. 5 plus 3Q, so it's sort of like a fixed cost amount of 5. Once you decide to start producing something, you're in it and you're running the $5 overhead. From there, it's $3 per unit in terms of marginal cost. So as an outline, or as a sort of problem formulation, we could look at it like this. I'll take all of our information. We're going to maximize profits. The choice we get to make is the price level. And in terms of sort of constraints or the mathematical information or the data that's going to help us choose the best price level to maximize profits, it's the demand curve that tells us the relationship between quantity and price, and then the cost function, which tells us the relationship between cost and quantity. And so if you wanted to think about this mathematically, costs are related to prices through Q, right? So the cost adjusts when the quantity adjusts. The quantity adjusts when the price we set adjusts. So in some ways, by setting higher prices, I think you'll see that we can lower our costs, right? So if we raise the price, the quantity we sell lowers, that lowers cost. In terms of functions, it looks like this: revenue minus costs is the profit definition. The revenue definition is just P times Q. And if you substitute the demand curve in for Q, then you would have 10P minus P squared. The cost function also has Q right here, so we could substitute in the demand function there and get 5 plus 30 minus 3P. And so you could rewrite the profit equation like this. The revenue piece and the cost piece, take the difference in those, and you get the profit equation. So, why are we doing calculus, or why is economics basically an applied calculus problem for many situations? Well, if we have the underlying profit function, then calculus tells us exactly what to do with that kind of problem. Let's look back at it. You have a variable p. It has a squared term, a linear term, both here in the negative 3p and here in the 10p, and then it has a term that has a zero exponent, or whatever you want to think of it as, but price doesn't enter. So it has sort of this classic quadratic, and we know what to do. We have a quadratic and one variable. You take a derivative of that function. You take a derivative with respect to the variable, solve it for 0. That's essentially the flat tangent idea. And then you know that's the best choice, right? Because that's the point at which the marginal is not adjusting. The marginal profit is 0. You're no longer making gains to profits, and so you set that price. One addition we have in economics that you may have learned in your study of supplier production: if profits don't cover the variable cost, then we should get out. We should exit production, because we have a bad margin situation and we can't make anything up on volume. Now, profits, if they cover variable costs, may help us recoup some overhead or some fixed costs, and so they may not be covering everything, but as long as they're covering something. But if the variable cost, the cost that we can avoid, are too large, then we have to shut down. Okay, we said the 101 solution from economics was marginal revenue is equal to marginal cost, so we need to actually identify that from our result here. It's this from calculus. You could take the derivative of profits. Let's just call those marginal profits, right? If you took the derivative of anything, it's really the marginal of it. Setting that equal to 0 is the same thing as saying the marginal profit is 0. You get no gain from an additional adjustment to your choice variable. But another way to write marginal profit would be marginal revenue minus marginal cost. And so it must be the case, if setting marginal profit equal to 0, and we can rewrite it this way, well, forget the middle part here, MR minus MC equals 0. That's the same thing as the calculus or the economics 101 rule that they told you, and they told me, and they told everyone, but they wait for a long time before they tell you why it works that way. Okay, so let's go back to our problem. Marginal revenue equals marginal cost. Differentiating with respect to the price P, you can do the marginal revenue side first, 10 minus 2P. The marginal cost side next. Marginal cost equal to negative 3. And then just set those two equal. You'll find that 2P must equal 13, so P star, the best price to charge, 6.5 in that problem. You get Q star equal 3.5, and then I think I have a spreadsheet, so let's switch over and look at that real quick. Okay, in your spreadsheet for this week, in the contents here, you see that the marginal revenue, marginal cost example is available. So if you want to see the formulas here, if you want to try changing some assumptions, you can do that. Here's the market price assumption that's built into the total revenue. You can see that formulas have been entered here for the change in revenue, the change in cost, and for profit. So you could try out some of those, but the one we're on right now is this profit equation. So we have a function, profits, being plotted here against the price that we choose, right? So the objective and the choice, and you see here what the profit function looks like. And so if we were talking about that derivative, the change in profit from a change in the price, well, when we say that is equal to 0, what it really is saying is you hit this peak up here, and if you prefer to think of it in terms of tangents, there's a tangent line that's flat or has a slope equal to 0 at the top of this. Yeah, and so the model here, so this is a graph of the problem, so you can see the solution, but let's go ahead, and I've built the equations up here. So I've got the demand equation here with its intercept and slope. I've got the cost equation here, again with its intercept and slope. I've got a definition for revenue that says multiply the price times the quantity, and I've got a definition for profit that says subtract cost from revenue. And so we could actually just solve this problem really quick. Let's just use solver. And so we'll go, I think this is the first time we're using solver in this class, though we're going to use it a couple times in this module. So let me show you how to use solver. as a sort of an introduction, and then when you get to the lab you'll have some steps that take you through it a little more clearly. But let's go to, in Excel, you can open this spreadsheet and go to Data, and over here to the right under Data, so this is the Data sort of menu, and then on this ribbon go all the way over to Analysis and find Solver. And if you don't see Solver there, you'll need to make one extra step beforehand, and that is to go to File, go down to Options, and then go to Add-ins. Okay, so once you get to Add-ins, you'll see that the Solver add-in is there. If you click on it and click on OK, it'll give you the options to install it. I already have it installed, so I can't do it, but that's where you go and find it. Okay, so I already have it, and in fact this spreadsheet already has the information collected in it, but this is what Solver looks like. And I'm sorry, there's no way for me to make this larger. That's why there's a handout that has all the steps cut out a little bit later. But what I'm doing here is, it says you can set the objective. That's the first thing you can choose. So I'm going to set the objective cell to be the profits in B13. The next thing it says is, what do we need to do with that objective? Maximize it, minimize it, or set it to some value. We're going to maximize that. And then it says, which variables are you going to be changing? Well, we only have one variable to change, and that's price, and it's in B1. And so if I click on this number or this little red arrow, it'll show me that B1 has been selected. We're not going to do anything else right now to this. We'll learn about how to add constraints, what this means, but for now we need this to be nonlinear, right? So I'm choosing this GRG nonlinear solution method because this is a curve, right? So most of our problems are going to be straight line with these corner points, but for this one it's a curve, and so we'll just click Solve, and hopefully it agrees with me, and it does. Okay, so this went to my other screen, but I'll show it to you here. It says Solver found a solution, optimality condition is satisfied, and it tells me it could show me some reports or anything. With that, I think we'll shut down this this lecture and move on to our next topic. There is a quiz following this, so you'll want to look at that. It'll let you play with the spreadsheet just a little bit more.